Hello, I am Sarita Yadav and this is my term paper presentation for the course PHY 402 and I am going to discuss about Ising model, a model of ferromagnetism. So the very first question that we can ask is what is an Ising model? Ising model is basically an array of lattice sites. So these are the array of lattice sites with only the nearest neighbor interaction. So if I consider this lattice site, it only interacts with the neighboring 4 lattice sites. And it also depends on the manner of occupation of the neighboring sites, whether the neighboring lattice site is upspin or downspin. On each lattice site lives a quantum spin that can sit in either spin up or spin down. Like the red lattice site that I have marked is spin down, and this is spin up. If it is spin up, we say the eigenvalue is +1, and if it is spin down, we say the eigenvalue is -1. Now we'll apply magnetic field to the system. For any two adjacent sites ij, there is an interaction and each site has an external magnetic field. The Hamiltonian of the system can then be written as this, where J is the exchange energy and J is the exchange energy. And this term is because of the magnetic field. What is exchange energy? Is the energy released when two or more electrons with the same spin exchange their energy or exchange their positions. Like if these two same spin electrons or the lattice sites exchange each other, they are indistinguishable. We cannot distinguish them. So the energy because of this is called the exchange energy. J is the exchange energy and it occurs between identical particles which are indistinguishable. This effect is due to the wave function of indistinguishable particles and is a quantum mechanical effect. J is greater than 0 if they are aligned parallel, both up or down, and this is the condition of a ferromagnet. If J is less than 0, they anti-align, one an up spin and the other is down spin, and this is known as an antiferromagnet. Now we'll move on to the one-dimensional Ising model. So basically here we'll discuss about the Ising chain. Ising chain is, I have shown the diagram here. So this means that if this is the first lattice site, this is also the n+1 lattice site. Now the Hamiltonian can be written like this because one-dimensional Ising model will only interact with its nearest neighbor. Now that we have written down the Hamiltonian, we can write the partition function, which I have not explicitly written the equation of that, but we know that it is minus e raised to power beta h, summation over e raised to power minus beta h. From the partition function, we can calculate many macroscopic quantities of the system, like the Helmholtz free energy, internal energy, magnetization susceptibility, and so on. When we write down the partition function, we can even adopt the quantum mechanics notation and define 2x2 matrix, which is the T matrix and transfer matrix. So this is what the transfer matrix comes out to be. And we can calculate all the macroscopic quantities from this. Now we'll switch on to the two-dimensional Ising model. So I have split two-dimensional Ising model in low temperature limit and high temperature. So for simplicity, I have set B equal to 0. As I've set B equal to 0, the second term in the Hamiltonian here is 0. So Hamiltonian just depends on the exchange part. In low temperature limit, T tends to 0, so beta J will tend to infinity. The partition function can be approximated by the sum over the first few lowest energy states. So we know that at low temperature, nothing is disordered. All the sites are ordered. There is no randomness. The first lowest energy state will be either all the spins are up or they are down. I have shown all spin up, see, all spins are up here, and the E is equal to E naught is minus 2nj. So we can calculate the energy from the Hamiltonian. and this is just a factor of j. Factor of j just comes here because we have set v equal to 0. Now the next excited state will be when one spin is down, that I have marked in red here. So this is when one spin is down. So this is so we know that Ising model depends on the manner of the occupation of the neighboring sites. If it is down, it will cost an energy of 2j, and it has 4 neighboring sites, so it will cost an energy of 8j. So E1 will come out to be E0 plus 8j, and it has a degeneracy of n. Now when we say the second excited state, it will be when 2 states are down, 2 spins are down. Now they are interacting with 6 neighboring lattice sites, so the energy cost will be 12j, and E2 can be written as E0 plus 12j with the degeneracy of 2n. So now we can write the partition function from all this information, and it comes out to be this. This is two-dimensional Ising model at high temperature. At high temperature, everything is disordered. There is no ordering. There's no ordering. At high temperature, we expect the partition function to be dominated by completely random orientations. And when we know the disordered configuration, when everything is random, it has maximum entropy. So the partition function can be written as this because we have already set p equal to 0. And from all, when we expand this and do the high temperature approximations, we get z equal to this. I have not shown the derivation, but I have done this in my term paper. You can check it out there. Now the next thing will be connection between the high temperature and low temperature limit. So the connection between the high temperature and low temperature limit is done by the Cramer-Vanier duality. It relates the free energy of a 2D square lattice Ising model at low temperature to that of the Ising model at high temperature. So we know that at high temperature, partition function is dependent on tan hyperbolic. It is a function of tan hyperbolic. Whereas at low temperature, it is a function of some exponential. So we'll equate these two. E raised to power minus 2 kc is equal to tan hyperbolic kc. From here, we can calculate that kc is 0.4407, which turns out to be correct from Onsager's exact solution. Now we'll turn into the end of the presentation. That is the critical behavior. So I have shown this figure here. At 0 temperature, every spin is aligned in either spin up or spin down. Now when we increase the temperature, but we still keep it below the critical temperature, some spins start orienting in opposite direction. Now if I consider that this blue ocean is basically, the blue portion is basically the ocean of spin up. Now these red dots that you see here are basically spin down particles or spin down states. Till 2.26 temperature, which is below the critical temperature, you see much more blue portion, that is more spin up states rather than spin down states. Now each connected red dot here you see is basically a cluster. And the typical length scale of cluster forming is called the correlation length, and it grows as we go beyond the critical temperature, and it diverges at the critical temperature. When we go beyond the critical temperature, the correlation length starts decreasing again, and at infinite temperature, it again becomes 0. So this is the end of the presentation. Thank you. If you have any doubts, you can refer to my term paper as well as contact me. Thank you.